Welcome to this explainer. Okay, today we are diving headfirst into the absolute heart of computer graphics. The core problem we're looking at is essentially one giant, beautiful illusion. How do we trick the human eye into seeing absolute perfection, all while operating under a punishingly tight computational budget? I mean, every single millisecond counts when you're rendering a digital world at 60 frames per second. The sheer ingenuity researchers use to make this happen is just absolutely fascinating. Okay, let's dive right into this by defining our fundamental enemy in digital rendering, aliasing. So, aliasing is basically a side effect that pops up whenever a digital sampler tries to digitize real-world information. The source material draws a really great parallel to audio sampling here. In audio, signal processing relies on the Nyquist rate to avoid aliasing. But in image rendering, trying to hit that perfect rate is just way too resource-intensive. Because our screens are made up of square pixels, trying to draw smooth, real-world curves inevitably gives us those harsh, jagged stair-step edges we've all seen. Digital signals just fundamentally struggle to match the infinite resolution of reality. So, what does this all mean? It brings us to the central question of our explainer today. How in the world do we take those blocky, aliased pixels and turn them into breathtaking, photorealistic worlds in real time? We're going to trace the evolution of how we solve this, starting from basic rasterization tricks all the way up to the cutting-edge AI that's completely redefining the industry today. Here is the roadmap for today. First, the digital jaggies problem, then the anti-aliasing arsenal, next up, the path tracing challenge, followed by reconstructing reality, and finally, the AI rendering revolution. Section 2, the anti-aliasing arsenal. When we look at modern engines like Unity's high-to-finish render pipeline, we constantly run into this classic cost versus quality trade-off that pretty much governs all computer graphics. Visual quality always demands an economic price from your hardware. First up, we've got FXAA, which smooths things out on a per-pixel level. It's incredibly fast and cheap, but it kind of blurs the final image and struggles a bit with shiny specular lighting. Then there's TAA, or temporal anti-aliasing. This uses a history buffer to smooth objects in motion. It's great, but it can definitely leave ghosting artifacts behind fast-moving objects. SMAA looks for border patterns and blends them, giving you really sharp results, but honestly, it's best suited for flat or clean cartoon styles. And finally, MSAA, which actually samples multiple locations within every single pixel. Now, MSAA is fantastic because it legitimately solves the core spatial aliasing problem instead of just blurring over it. But wow, look at the cost. It is incredibly expensive for the GPU. In fact, it is so resource-heavy that turning it on forces the game engine to literally disable other beautiful features, like screen space reflection and temporal anti-aliasing, just to keep a playable frame rate. This is exactly why you so often have to choose between a smooth image or beautiful reflections in your graphics settings. Section 3, the Path Tracing Challenge. If we want true photorealism, we really have to move beyond just hiding jagged edges. We actually have to simulate the physical behavior of light. This is called path tracing, and let me tell you, it is an incredibly computationally heavy beast. And this brilliantly illustrates the sheer scale of the challenge here. On one side, we have a pristine, photorealistic reference image calculated with 4,096 light samples per pixel. It's absolutely perfect. But on the other side, that's what a real-time graphics card can actually afford to calculate in a fraction of a second, just one sample per pixel. It is an extreme, static-filled, unrecognizable mess of noise. I mean, the lion's face on the wall is completely lost. As the source research points out, reducing that noise to imperceptible levels without any post-processing requires thousands of samples per pixel. But because real-time desktop GPUs can currently only afford about one single sample per pixel while maintaining high frame rates, raw path tracing is fundamentally impossible to run on its own. We desperately need a brilliant mathematical solution to bridge the gap between that noisy mess and that perfect image. Section 4, Reconstructing Reality. To clean up that one sample per pixel mess, researchers developed an algorithm called Blockwise Multi-Order Feature Regression, or BMFR for short. The BMFR pipeline works in 4 main steps, and the researchers outline a brilliantly smart approach here using what they call feature buffers. See, even though the lighting in our one sample image is a total noisy disaster, the game engine still knows the exact geometric shape of the objects, the surface normals, and the base colors. BMFR uses these noise-free feature buffers to guide the cleanup process. This ensures that it removes the noise without accidentally blurring away the sharp edges of the actual 3D geometry. It's so smart. The first step is temporal accumulation. Basically, the algorithm looks back at previous frames and reprojects that historical data onto the new camera frame. By mixing a percentage of that old accumulated data with the new noisy frame, it instantly increases the effective sample count and dramatically reduces that awful temporal flickering. That historical data then feeds directly into step 2, QR factorization. Now, this is the mathematical heavy lifting. The algorithm breaks the screen down into tiny, non-overlapping blocks, usually 32 by 32 pixels. It then attempts to mathematically fit the clean feature buffers to the noisy image data within each specific block. Traditionally, this kind of regression was way too slow for real-time graphics, but this surprisingly fast QR factorization implementation makes it totally viable on a modern GPU. Now, what's really interesting about this slide is the incredibly clever math hack the researchers had to invent to make this work. It's called stochastic regularization. Sometimes the feature data in a block is rank deficient, which is just a fancy way of saying there isn't enough variance in the math, and that would normally cause the factorization to crash by dividing by 0. To fix this, the algorithm intentionally injects a tiny amount of mathematical noise, zero mean noise, into the clean buffers. They literally added noise to fix a noise problem. It perfectly stabilizes the math without ruining the final visual output. Because that QR factorization transformed our data into a much smaller matrix. Step 3, back substitution, is lightning fast. By dealing with this reduced mathematical footprint, the algorithm solves the linear least squares problem in a fraction of a millisecond, figuring out exactly how to reconstruct the lighting for that specific block of pixels. In step 4, the weighted sum, the whole pipeline brings it all together. It applies those mathematical solutions calculated in the previous step and blends them using those pristine, noise-free buffers like our surface normals and world space positions. This synthesizes that wildly noisy one-sample input into a beautifully clean, recognizable image. But we aren't quite finished yet. Because BMFR processes the screen in those rigid 32 by 32 non-overlapping blocks, the raw output can sometimes look a bit like a grid. So, a second round of temporal accumulation is applied. The system dynamically blends about 10% new data with 90% old data, all while shifting the processing grid with random offsets each frame. This perfectly hides those blocky artifacts. Finally, the pipeline wraps up with a familiar friend, a temporal anti-aliasing or TAA pass for a final polish. Interestingly, researchers noted that while adding TAA at the very end sometimes slightly lowers the objective computer-graded metric scores of the image, it overwhelmingly produces the most visually pleasing, stable result for the human eye. Section 5. The AI Rendering Revolution. So, while BMFR is an absolute incredible mathematical achievement, research from experts like Edward Liu highlights a massive paradigm shift happening right now. Neural networks and diffusion models are rapidly taking over the heavy lifting. We have PixelDit, an end-to-end diffusion transformer that learns directly in pixel space. Smooth Diffusion VE is doing real-time, temporally consistent generative video editing. ExtraNet uses neural networks to predict accurate shading on extrapolated frames, which lowers latency while boosting frame rates. And of course, the absolute powerhouse that is DLSS4. So the crucial point is this. Technologies like DLSS4 are fundamentally changing the game. Instead of relying on manual algorithms like BMFR to try and guess how to clean up a noisy path-traced image, DLSS4 uses transformer-based neural networks. These AI models have already been trained on supercomputers to understand exactly what the high-resolution, perfectly ray-traced world should look like, and they simply predict and generate the missing pixels and lighting details in real time. Which leaves us with a truly fascinating conclusion to ponder. As AI models become faster and even more deeply integrated into our graphics hardware, will all that incredibly clever traditional rendering math we've explored today soon be entirely replaced? In the very near future, when you explore a breathtaking photorealistic digital world, will it be calculated by geometry and regression, or simply dreamed up and hallucinated by artificial intelligence? It's an absolutely incredible time to be watching this space. Thank you so much for joining me on this explainer, and keep your eyes on the pixels.